Let's look at an example that will involve elastic potential energy as well as work. So a spring is going to be used to launch a 500-gram mass straight up in the air. We find that when the spring is compressed 30 centimeters, the mass is launched 2.5 meters above the height where the spring is compressed. We want to use this information to determine the spring constant and how much work you needed to do when you compressed the spring to then let it fire the mass. So we'll start with part A, determining the spring constant. This is a conservation of energy problem, so the first thing I want to do is define my initial and final moments. My initial moment will be when the spring is compressed, so the mass is at rest and the spring is squished. And this dashed line here, I'm going to define the squished spring height as a height of 0. I can choose anything convenient as my height of 0. My final moment will be after the spring has sprung, so the spring is now relaxed, and the mass is at its highest point, so the mass is at rest at the final moment, and it is now at a height of 2.5 meters. After the initial and final moments are defined, I want to define our system. That will tell me what kinds of energy we can talk about. And I'm going to have the mass, the spring, and the earth all as part of my system. Including the spring means I can talk about elastic potential energy. Including the earth means I can talk about gravitational potential energy. If my system were just the mass, I could do that. What it would mean is then, instead of elastic potential energy, we would have work done by the spring as it expands, and instead of gravitational potential energy, we would have work done by the Earth through gravity as the mass moves upward. Instead of worrying about all of that, I'm going to take the spring and the Earth to be part of my system. Once I do that, I can look for any external forces that might do work, and with this choice of our system, there are none. If you think about the free body diagram for the box, it would involve a force exerted by the spring, but the spring is part of our system, so that is an internal force. And it would involve the force of gravity, but the Earth is part of our system, so that is also an internal force. I can now go to our general conservation of energy equation. Initially, the box is at rest, so there is no initial kinetic energy. Initially, the height is 0, so there's no gravitational potential energy at the start. The spring is compressed 30 centimeters, so we have 1/2 k squish squared as our initial elastic potential energy. No work because there are no external forces acting on our system. At the final moment, the box is again at rest, so the final kinetic energy is 0. It does have gravitational potential energy, mgh, and now the spring is relaxed, so the elastic potential energy at the final moment is 0. I can solve all of this for the spring constant k, and we get 272 newtons per meter. Moving on to part B, how much work do you need to do to compress the spring? I'm going to pick new initial and final moments. Here my initial moment will be the box first being set on top of the spring, so the box is at rest, but the spring has not compressed at all yet. The final moment will be once the spring is compressed 30 centimeters, and the box is again at rest, ready to be fired. I'll use the same system, the mass plus the spring plus the Earth. Any external forces that might do work? Yes, in this case, the force that I push down with when I compress this spring will be an external force that does work. So the force of my push is exerted by me, and I am not part of the system, so I'm an external force that does work. Setting up our conservation of energy equation, always the same equation we're working with. Everything is at rest at the start of the problem, so no kinetic energy. The box starts out 30 centimeters above my h equals 0 line, so mgh is the initial gravitational potential energy. At the start of this problem, the spring is not compressed, so no EPE in the beginning. I want to figure out the work that I do on the spring to make it compress. At the end, at the final moment, nothing is moving, so kinetic energy is 0. The height of the box is now 0, so gravitational potential energy is 0. And we have elastic potential energy, 1/2 k that we just found, times the squish squared. solving this for the work I do on the system, I find that I do 0.8 joules of work. Thinking for a moment about the sign, we get that the work I do is positive. That makes sense for two reasons. One, positive work means that the system increases in energy. So as I'm squishing that spring, I am increasing the energy of the mass spring Earth system so that when I let go, it can fire the mass. Anytime the system gains energy, that should mean the work done on the system is positive. That's what we see here. Another way to think about the sign of the work, when I push down to compress the spring, the force will point down and the displacement will also be down. Anytime the force and the displacement are in the same direction, that also results in a positive work, which is what we are seeing here.